All right, everyone. Right off the bat, I see a slight little typo on my announcement slide because that's supposed to be 8.2. Let me say one quick thing about the homework. The homework that was due today, I posted something in Teams about matrix math. If you're using an older version of Excel, there's a little trick that you have to do if your Excel version is older when doing matrix math. If you do it like we did in class and you press enter, like you type a formula in and you press enter, sometimes it can get a little squirrely on you. And so the way that you have to handle that is you have to highlight the entire region and then hit Control-Shift-Enter. I might record a really short video if there's any questions on that. But if you go to Microsoft Teams, I posted a link where in a previous course I taught a couple years ago, I showed how you do that in Excel, and it's really easy. It's not very difficult. If you understood everything we did in class Wednesday, then this is going to be pretty straightforward. But if anybody has any questions, let me know. As a result, I'm not going to assign any late penalties for this homework 8.1. So if you need a little bit more time to get it done, that's fine. But this homework's very fast. I mean, anybody who did the homework knows it really didn't take all that long to do. You just, put it in Excel, do your formulas, and submit the file. It probably took you all of about 5 minutes. So I'll accept those through maybe like, the end of the day, or if there's anybody who really needs more time, let me know. Today, what I want to do is I want to finally start digging into the world of matrix analysis, and I want to do a problem start to finish using matrix analysis procedures. Now, I'm going to show you right off the bat the flow chart for matrix analysis. And I know the first time you see it, you're going to go, oh my God, it looks horrible. It's really not that bad. So this is really the process. And the way I think of it is really like 4 steps. And some of these steps are much faster than they look. So if you look here at the flow chart, I think the top 2 boxes are things that you're familiar with. So if you go back to when we used RISA, or I mean, you could even have this discussion independent of a particular software package. But the idea for solving a structure using a computer program is the first thing you have to do is you have to create the model. And so what does that mean? It means, we have to establish the geometry of the model. So we need to know where the joints are. We need to know where the members are. We need to know what the boundary conditions are. Is a support hinged or pinned? Is it a roller? Is there a fixed end? All of that. We need to understand the loads. And so in RISA, really we're talking about 2 different types of loads. And this isn't just RISA, again, this is just the process. There's loads that can be applied to the joints, and then loads that can be applied to the members. And then finally, we have to define the stiffness properties. We have to define the materials, the sections, all of that. And then once we do that, we hit this little button, this little equals button, and then the equals button spits out the stuff up here. So, we understand how to do this, and then we press the equals button, and it gives us that. It gives us the support reactions. It gives us the internal member forces. It gives us the deflected shape of the structure. It completely solves everything that we're looking for. But what we don't know, or what we haven't discussed up until today, is what happens when you click that equals button? What happens when the software program analyzes the structure? And because all software programs work the same way, I think this is a very valuable discussion. Now, there's a lot going on here on this slide, so let me just sort of break it down in a very digestible, process. So the first thing that we do when we define a model is we have a bunch of different members and loads and boundary conditions. So what a software program will do is it will take each member one at a time, and it will write what's called a K matrix or a stiffness matrix. And so it'll compute a K matrix for each member, and then it will assemble that into a K matrix for the entire system, right? So you have a bunch of these little K matrices for each of the members in the structure, and then you assemble it into one big K matrix for the entire structure. There's some details that aren't going to matter today, but we'll talk about next week about coordinate systems, about local versus global, but that'll become clear here in a little bit. But one thing I will mention, if you look at this flow chart, some of you are probably looking at this and it looks like maybe there's some typos. So for instance, you see some little f's and some big f's, or maybe some little deltas and some big deltas. those are not typos. There's a very specific reason why those are written that way. The long and short of it is that the little terms refer to local coordinates and the uppercase letters refer to global coordinates. But for what we're doing today, that's not going to matter. So you can treat all the F's the same, all the deltas the same, all the K's the same, they're all the same. And anytime that you see local versus global, that you can kind of ignore for today. Okay, so again, to go back to the process, we write a little K matrix for each of the members, and then we assemble it into a big old K matrix for the entire system. And so once we do that, we write the force vector for the system, which is going to be very, very easy. And so if you've got the stiffness matrix for the whole system and you've got the force vector for the whole system, you can get the displacements for the whole system. You just invert the K matrix, multiply it by the force vector. You have to reduce it based on your boundary conditions, but that's also very, very easy. Once you have the displacements, what you do is you take those displacements and you break them down into little displacement vectors for each element. And if you got the stiffness matrix for each element and the displacements for each element, just multiply and boom, you've got the forces in each element. And so the idea is, you sort of like collect the system into one big matrix, solve for your displacements, take those displacements, plug them back into each element. And then that's it, the entire problem solved. And so there's a very algorithmic process, if you will, where you can take a model and basically solve the entire thing out in one straightforward process. Now, you're going to find that this is really straightforward, and I've got a really simple problem today to sort of explain this technique. But before we begin, I want to institute some ground rules right now, because we're going to start talking about structures and thinking about these problems a little bit differently. And so in order to do that, I want to set some ground rules before we begin. So first off, okay, I want to talk a little bit about terminology. I'm going to use some terms interchangeably. And anybody who starts to delve into the world of matrix analysis and finite elements will do this. So if you see me use the term joint and node, they mean the same thing, okay? So all I'm talking about is just where two members intersect, or the ends of members. So like a member would have two nodes, one on each end, or an element would have two nodes on each end, which goes into the next point. I'm going to use the term member and the term element interchangeably. So they basically mean the same thing. In fact, even RISA recognizes this. If you go into joint coordinates, like you're defining the joints, and you just start using the automatic naming, how does RISA automatically name joints? It says N1, N2, N3, N4 because it's calling them nodes. So those are very interchangeable terms. Okay, so that's the first point. Second point are units. Okay, matrix analysis is very blind to unit conversions. So you need to convert everything to consistent units before you begin. And so in USCS units, that typically means that we're operating in kips and inches. We could operate in kips and feet. We could operate in pounds and feet. It doesn't matter. We just have to use a consistent unit system. So like with RISA offers the ability to change into whatever unit system you want, but it will convert to consistent units before it begins the analysis. So it always does that first, always operating consistent units. It will save you so much headaches down the line. Okay, the other thing that we need to talk about is the sign convention. Okay, so in matrix analysis, basically what we're doing is we're writing equations of equilibrium. And so if you go back to statics, when you write an equation of equilibrium, we say, okay, let's sum forces in the x direction, but when we write this equation, we're going to assume all the forces to the right are positive. Okay, so we're always going to consider forces to the right positive, displacements to the right positive. In the y direction, we're going to consider upward forces positive, upward displacements positive. And so that's that's something that you really need to like drill into the back of your head, that this is the sign convention we're going to use. If we wanted to talk about rotations, we typically express counterclockwise moments and counterclockwise rotations as positive, but we're really not going to deal with that in this class. Not that it's not anything you can't understand, it's just we're going to be limiting our discussion for matrix analysis to bar elements and trusses. And trusses, we don't have any moments or rotations, so it's not going to matter. So that's something that we just need to establish right now: the terminology, the units, and the sign convention. Just keep that in the back of your head. Okay. All right. Is this convention the same in countries that I'm going to say yes, because I'm getting this sign convention from a coordinate system, from graphing. So the x-axis points to the right, the y-axis points upward. That's where I'm getting that. The one thing that can change, and we've noticed this with RISA, is when it spits out your final output, if it considers tension positive or compression positive, things like that. That can change, but in the end, we do need to pick one coordinate system and stick with it. I'll say this, it doesn't really overall change the process, but the details that we are going to encounter throughout the analysis, if we don't pick something and stick with it, it'll get messy. Okay. All right. Now, one of the things I said a little bit ago is that you kind of need to start thinking about structures a bit differently. And so what I really mean by that is I want you to start thinking about a structure in terms of a new, this is a new term, what's called its degrees of freedom. Okay, so what is a degree of freedom? A degree of freedom is a nodal displacement. So if we're talking about a joint on a particular member in a structure, the idea is for that member, we're talking about the total possible number of displacements. And so here's sort of the easiest way to think about it. So let's take a look at a truss, okay? So if we're talking about a truss, and Matt, picture in your head a truss and picture a particular joint in that truss. Okay, if I'm looking at that joint and I'm asking myself, what are the different ways that truss could deform? Well, that truss could experience a displacement in the x direction, and it could experience a displacement in the y direction. So each joint in a truss has what we call 2 degrees of freedom. A degree of freedom in the x direction, a degree of freedom in the y direction. So when we look at a plane truss element would have 2 degrees of freedom per joint, but 4 degrees of freedom total. So like if you're doing a truss analysis in RISA and you build the model, you put the loads on and you run it, every joint will have a displacement in the x direction and a displacement in the y direction. Now, some of those displacements might be 0 if, for instance, you have a joint with a support reaction there. Like if I'm looking at this, if this truss right here, and I look at, this joint, and this one is pinned, right? Well, both of those displacements are going to be 0, but what we're talking about is the total possible number of displacements for a given element. So plane truss elements have 2 degrees of freedom per joint, or 4 degrees of freedom total. So if I were to look at the K matrix for a plane truss element, the K matrix would be 4 by 4, 4 rows and 4 columns. So a 4 by 4 grid of numbers. For a plane frame element, and a plane frame element is the general purpose element that RISA uses, it's going to have 3 degrees of freedom per joint, or 6 degrees of freedom total, because each joint could have a displacement in the x direction, a displacement in the y direction, and it could also have a rotation. So there's 6 total. And notice how I'm drawing all of those degrees of freedom according to what we're considering their positive direction. The horizontal terms go to the right, the vertical terms go up, the rotational terms go counterclockwise. The idea is that these degrees of freedom, these individual terms, fully define what the member looks like after it's deformed. So there's before it's displaced, you put the loads on, and then after it's displaced. So if you've got the nodal displacements and you want the displacement in between, you would just interpolate. And so, but with that, you can find the deflection anywhere, but really what you need are those unique values at the ends of each joint. Does that concept make sense? Because I really want you to start thinking about structures in terms of their degrees of freedom. Let me pull up my chat window here. Everybody good with that? All right. Okay, so let's talk about the simplest element to deal with, which is a bar element. And so the reason why we always start with bar elements when we first start looking at stiffness analysis is because the element only has 1 degree of freedom per joint. So for what we're talking about today, I'm not talking about forces that are going up and down. I'm not talking about moments or rotations. I really want to keep it basic and I really want to keep it simple. So I'm only talking about stuff that moves to the left or right. So all the forces and displacements that act to the right are positive, and all the forces and displacements that act to the left are negative. So the problem that I'm going to do, I want you to think in your head that all we're talking about is stuff moving to the left and right. I say here that all the members will be horizontal, and I know you're probably going to get upset at me because you're going to look at your homework and there's going to be members that aren't horizontal. But really what I want you to think about is when I say an element is one-dimensional, I mean, yeah, we're talking about force, we're talking about just horizontal forces, but I also kind of want you to think about that maybe a little differently. Really what I'm after is that each joint only has 1 degree of freedom. So you can think there's only one unknown displacement at each joint, a displacement at joint 1 and a displacement at joint 2. So for a bar element, the stiffness matrix is going to be 2 by 2, okay? And what I want to do is I want to see if we can define the stiffness matrix for a bar element. So that's this K matrix for the bar element. Now, one of the nice things about stiffness analysis is that once you've determined the expression for a bar, you can use that expression for any bar. And so the mechanics of it are really, really straightforward. And so when we're talking about bar elements, let's go back to mechanics. Let's go back to an axially loaded bar. So we talked about this before. So if we have a bar and it has some, cross-sectional area A, it's made of a material with a Young's modulus of E, and it has some length L, and I yank on it with some force F, it's going to stretch some amount delta, right? So the F is the force, the delta is the displacement, and the relationship between the force and displacement is this term stiffness. Now, if we're just talking about a stiffness value, that stiffness value is EA over L. Okay, but what I want to find is a stiffness matrix for this bar element. So what we're going to do for this this problem is we're going to basically sequentially set each of these degrees of freedom equal to 1, and then look at what the bar looks like, and then ask, well, what forces would cause that displacement to happen? Now, I'll walk you through what that means here in a bit, but there's really 2 things I want you to make sure that you have burned into the back of your head. The first, I want you to keep in mind, just burn this into the back of your head, that forces to the right are positive. Displacements to the right are positive. Just stick with me on that. The other thing that I want you to look at is this formula right here. What happens if delta equals 1? Okay, if delta equals 1, then your force is just EA over L. So there's 2 things I want you to keep in mind. The forces to the right, the displacements to the right are positive, and if delta equals 1, then F is EA over L. Okay. All right. Everybody good? Yes, Mr. Enoch.
What if we did, what if we were working on one of these problems and we did how we talked about a couple weeks ago, where you can just flip the cantilever beam like to the other side? So in that example, the support would be on the right. Would forces to the right still be positive?
That's a great question. The short answer is yes, because of the description, or the way that we describe local versus global coordinates, and the transformation between local and global coordinates will make a whole lot more sense on Monday. Let me put it like this. When you run an analysis in RISA, RISA doesn't know what you have defined in terms of a local coordinate system, right? Here's your problem. Here's 0, 0, and you're putting the truss, wherever. Everything's with respect to that common origin, right? Now, for a given member, you could have the coordinate system facing one way or the coordinate system facing the other. What we're going to talk about Monday is how we can map each one of these elements to a common coordinate system so that they're all referring to apples as opposed to apples to oranges. That discussion will make a lot more sense on Monday, but the short spoiler alert I'll give you, it's basically just all trig. But that'll become clear on Monday. Does that make sense? Okay. All right. So I want to look here on the board real quick. Okay. So I've got here on the board the two notes that I really want you to burn in your head. The idea that everything acting, all the forces and displacements acting to the right are positive, and then this term right here. If delta equals 1, then the force is EA over L. Okay. So if I look at a given bar element, so let's say here's the bar element. The bar element has 2 degrees of freedom. It has one right here and one right here. So there's 2, okay? So what we're going to do in order to derive the stiffness matrix is we're going to use what's called a direct approach. And the direct approach is basically literally yanking on this bar or compressing this bar and then recording the forces that cause those displacements. That's what we mean by a direct stiffness approach. We're actually compressing the bar or yanking on it. There are other approaches that we can use to derive the K matrix. There is a very famous approximate approach called finite elements. You know, the finite element method is just another way of developing this process. Okay, so let's take a look at this element. And I'm going to draw this down like this just so I have something to reference. Now I have 2 degrees of freedom. So if I have 2 degrees of freedom, what I'm going to do is I'm going to apply 2 different cases of analysis. So case 1 and case 2. So if I had an element that had 7 degrees of freedom, I would do this 7 different times. But since I only have 2, I'm only going to do this once. So for case 1, what I'm going to do is I'm going to set the first displacement equal to 1 and all others equal to 0. And so if I had, let's say, 7 degrees of freedom, I would say, okay, case 1 is delta 1 equals 1 and the rest equals 0. Case 4 would be delta 4 equals 1 and the rest equals 0. And then what I do is I manipulate the elements so that that displacement is 1 and then everything else is 0. And then I ask, well, what forces would make that happen? So follow with me on this. So here's the element. Now I want to draw the element such that the first displacement is 1 and the second displacement is 0. And remember, positive displacements are displacements to the right. So what would the element look like if the first displacement is 1 and the second is 0? Maybe it'll look like this, right? To where this displacement is 1 and no displacement here. Does that make sense? So I've taken this, I've got a displacement of 1 and a 0 displacement here. Does that make sense? Now, let me ask you this. Here's the element before I've applied the load. Here's the element after I've applied the load. Let's just keep this simple. What did I do to the element? How do you take a bar and make it look like this? What do you have to do to it? Scrunch it. You compress it. That's exactly right. So in order to do that, what I'm going to have to do is I'm going to have to take a force and load it in compression. So I have a force going this way and a force going that way. Okay, exactly right. Now, what is the magnitude of those forces? Remember, the displacement is 1. So what's the magnitude of those forces? EA over L, exactly. So this force is EA over L, and this force is EA over L. But there's one other thing to keep in mind. As Mr. Enoch, he said their magnitude sum to 0, and I want to follow along with that. Do I have this one over here written correctly, or am I missing something? That one right there. It's negative. That's right. It's negative. Why is it negative? Because it's going to the left, right? So this one's negative. This one's positive. Does that make sense? Okay. Let's look at case 2. Case 2, you would take delta 1 to be 0, delta 2 to be 1. So take delta 2 equals 1, take everything else, set it equal to 0. So what does the element look like with this equals 0 and this equals 1? Well, this stays here. This moves 1 to the right. Okay, so that means the element kind of looks something like this, right? So that dimension right here, that delta, is 1. And so if this is what the element looked like before, and this is what it looks like now, what did I do to the element, right? How do I get the element to go from this to that? Tension, right? So I have to yank on it. So following the same logic, this is negative EA over L because it's going to the left. This is positive EA over L going to the right. So what do you do? What is a stiffness matrix? A stiffness matrix is just a collection of these terms in a table, right? So what does your stiffness matrix look like? EA over L, negative EA over L, negative EA over L, EA over L. That's your stiffness matrix for a bar. It's that simple. In fact, what we are doing, because a lot of times it's a lot easier to do this, to write it out, is instead of writing all the terms EA over L in the matrix, we just say it's EA over L times all of these. So that what I do, I put all this on this slide, but I really wanted to sort of walk you through it because I thought that was really important. That is the stiffness matrix for a bar element. And for those of you that remember the properties that we discussed about matrices on Wednesday, what can you tell me about this stiffness matrix in terms of its properties? You'll see that on Monday. Don't worry. In fact, actually, you'll see that today. Just wait. Just wait. Because there's upward forces, there's all sorts of other stuff. Just wait. It's symmetric. That's the key. Stiffness matrices are symmetric. Always, no matter what, stiffness matrices exhibit symmetry. Okay. Now, if you're okay with this, what I want to do is I want to jump right into a problem. Okay, I want to jump right into this and see as far as we can get, because this is really the kicker here. So we're going to use matrix analysis to solve this problem, and we're going to try and completely solve it. And I'm going to try and walk this through as expeditiously as possible. But I think you're going to find this is really, really slick. Okay, now a couple things. I've already converted all of the units to kips and inches. So the members are like 180 inches long, 120 inches long. I've already done all that. And then I've got joints 1 and 4 are restrained. So their deflections are 0. And remember, we're only considering forces and deflections in the x direction. Okay. So let me go to the notebook because I really want to try and knock out some of what we got going on here. So Okay. So bear with me. I'm gonna do some stuff here. So here's the problem. Let me see if I can knock some stuff out pretty quickly. Okay. So let's take a given member, because one of the things you'll find is that this process is very, very, very repetitive. Okay. So so let's take this member right here. Okay. So I want to determine the EA over L for this member. So we'll call it EA over L for member 1. Okay. And again, all the units are converted for me. All that's taken care of. So I've got 2,000 KSI, 6 inches squared over 120 inches. So 2,000 times 6 is 12,000 divided by 120. That's going to be 100. 100, not 1,000. 100 kips per inch. Okay. So this is going to be, so if we wanted to write out its stiffness matrix, we could say its stiffness matrix is 100 minus 100 minus 100 and 100. That could be its stiffness matrix. Okay. And similarly, if we wanted to do this one, or we wanted to do this one, we could do the same thing. Okay. We could, chug it out. And I'll go ahead and tell you what you get is you get that EA over L for the second one, it ends up being 200. And EA over L for the third ends up being 100. So this is 200 and this is also 100. Okay. Is everybody with me on the concepts and the ideas? Are there any questions that are fuzzy now? Okay. All right. So like I said, this is just formulas. This is just plug and chug, just EA over L and writing out this matrix. Okay. So I want to go back to this flow chart. Okay. And I know this thing looks nasty, but there's a lot going on here that's either that we can ignore for now or has kind of already been done for us. Okay. So for instance, maybe I'll write this out here. So I'll say note. For 1D bar elements, and this is going to become a lot more clear next week, but we can ignore local and global because that's gonna become much more important for trusses. So we can ignore any reference to local and global and treat lowercase and uppercase terms identically. And the last thing is that for 1D bar elements, there are no member loads. Kind of like a truss. So like, you know how with a truss, we only apply the loads at the joints. So if you look at this flow chart, that's going to make this process a lot easier. Like for instance, we're not going to have to worry about that because we don't have any global coordinates. Don't have to worry about that. Don't have to worry about that. We don't have to worry about this. Don't worry about that. And again, all these deltas and whatnot are going to be identical. But let me show you how this works. Okay. So if you look here, I cheated a little bit, and I'd already written some of this out. Okay. So what I want to do is I want to look at this structure a bit more globally. All right. For this problem. Now, as Mr. Enoch said, he was right, 2 DOF per member. Okay. In other words, each member is going to have one displacement here and one displacement here. But how many displacements for the entire structure? See, I propose that the entire structure has 4 degrees of freedom. In other words, here's what RISA or the computer would look at, and each of these joints is going to have 1, 2, 3, 4. Now, if we're thinking about this in terms of displacements, I can tell you what 2 of those are without doing any math. I know that the displacement at joint 1 and the displacement at joint 4 are 0 because those are supports. But the entire structure is going to have 4. Does that make sense? So if I go back to those little element stiffness matrices, right? So this was element 1, this was element 2, this was element 3. Maybe what I should do is I should write them like this. I should say, element 1 had a stiffness matrix of 100, minus 100, minus 100, and 100. But really what also needs to be indicated is element number 1 connects from 1 to 2, right? Stiffness matrix 2 goes like that, because that second member goes from degree of freedom 2 to degree of freedom 3. Same thing here. Does that. Does this make sense, this concept? These little numbers are called DOF codes. Now, Mr. Enoch said he was like, well, how can it be more than 2 by 2? For each bar, stiffness matrix is 2 by 2, but really what I care about is the K matrix for the whole system. And I propose that the K matrix for the whole system is going to be 4 by 4. And so really what we need to do is fill that in. That's what we need. This is what we call the stiffness matrix for the whole system, right? This K1, K2, K3 is the one for each member, but what we really need is the stiffness matrix for the whole system. Now, in order to do this, Here, that's a great question. The reason why is because remember at the beginning, I want you to think about this in terms of degrees of freedom. The size of the stiffness matrix. So the size of the stiffness matrix is with respect to the degrees of freedom. Now, remember, this problem, we're only considering displacements in the x direction, okay? If we were considering displacements in the y direction or displacements in the z direction, then the problem would get a lot bigger. But in the x direction, there's only, one here, one here, one here, and one here. I'm just thinking about the nodal displacements in the x direction. So the entire system has 4. Does that make sense? And admittedly, for trusses, it's going to get a lot bigger. Does that make sense? All right. Now, how do we take these and turn them into this? Okay. Like the Avengers, we assemble. Now, how does assembly work? Okay. Assembly is basically collecting all of the like terms into one big K matrix. So let me show you how this works. Okay, let's take this K matrix. All right, see how the codes are like 1, 2, 1, 2? So what do? I put those terms where they go inside the stiffness matrix. Okay, now what happens to the next one? Okay, so let's look at the next member. Let's look at this member. All right, so I start labeling them in. So this is negative 200, this is negative 200, this is 200, but oh, what happens right there? What happens right there is I've got 2 terms lapped on top of one another, right? And so in this instance, I would add. So I'll tell here in a second. I'll tell you why that works, and then we'll go through the process. All right. Same thing with this one. Simply place those terms where they go inside the global matrix based on those codes. So this would be negative 100, negative 100, 100, and then same thing. We're going to have an overlap right there. 200 plus 100. Okay. I propose that what you see right here, this is the stiffness matrix for the entire system. Okay, so if I wanted to rewrite that, I'd say 100 minus 100 minus 100, and then this would be 300. This would be 300. That'd be 100. And every other term would be 0. Now, that's the assembled stiffness matrix for the whole system. Why do we overlap those terms? Why do we add them? The reason why we add them goes back to the process I did here on the board, right? If I were to physically grab the structure right there and yank that joint over one, if I were to pull it to the right, 1 unit displacement, not only am I stretching element 1, but I'm compressing element 2. So at that particular point, those stiffness terms overlap. It's another reason why the other terms in the matrix are 0, right? If I'm yanking joint 1, that doesn't affect joint 4 at all, which is why all of these terms right there, which is why all those are 0. Does that make sense? I want to make sure this is clear. Okay. Simplifies the bar a lot. There you go. Okay. Now, I'm going to be lazy here. I want to show you something. Now, I want to show you something real quick. Let's see if we can write the force vector and the displacement vector. Now, let me show you what I mean by that. All right. So 1, 2, 3, 4, 1, 2, 3, 4. Okay. Now look at this. Let's look at this problem. I don't know about you, but I don't know the forces right here and right here. Okay. Those forces are unknown because they're support reactions. See, I propose the force here is going to be R1 and R4, right? I don't know what those are. But for the other two, watch what I'm going to do. I'm going to say 300, and I'm going to say minus 125. Why am I saying positive 300 but minus 125? Because of the direction. 300 goes to the right. That's positive. 125 goes to the left. That's negative. Now, we get sort of an inverse answer on the displacements, right? I don't know what delta 2 is. I don't know what delta 3 is. I don't know the displacements on these two joints in the middle, but I sure do know the displacements at 1 and 4. They're 0. So think about this from a computer perspective. I'm assembling a stiffness matrix using an algorithmic process. I'm assembling a force vector, and I'm assembling a displacement vector. Does that make sense? So if I wanted to write the entire system out, the entire system, remember, the entire system is K delta is F, right? That's the whole system. So we'd have 100 minus 100, 0, 0, minus 100, 300, minus 200, 0, 0, minus 200, 300, negative 100, 0, 0, minus 100, 100. And then the displacements, 0, delta 2, delta 3, 0. R1, 300. R4. Is that a fair way of looking at the structure? Now, before we call it, okay, I want to say one thing. I'm doing homework, but I'm going to make it due on Wednesday instead of making it due Monday because we're not done with this problem and I don't want to rush through it. So your next homework is going to be due Wednesday. But, and we're going to probably just pick up Monday and sort of finish this problem. But I want to ask two questions before we call it today. What property can you tell me is true about this matrix? That was true before. Mr. Riggs sort of pointed this out before. But what's the deal with this matrix? Yes.
I noticed that if we did like a transpose, I believe is the phrase, it would be basically almost roughly the same.
Yes, and there's a name for that. It's symmetric. The stiffness matrices will always be symmetric. And as Mr. Ball pointed out, he's exactly right. Now, you want to see something really crazy? Watch this. What is this plus this plus this plus that when you add them up?
0.
That plus that plus that plus that.
0 again.
What about plus that plus that plus that?
Same answer.
See, the reason why is because we respected a sign convention right off the bat. We said forces to the right must be positive and forces to the left must be negative. Remember, when you write a set of matrices, all you are doing is it's just a simple way of writing equations. These are all equations of equilibrium. The stiffness matrix is just the coefficients, right? So they all the rows and the columns have to add up to be 0. It's a check to see what you're doing is correct. In fact, when you look at your forces at the end, when you sum up the column of force vectors, once we figure out what R1 and R4 are, guess what? 0. So what I want to do is I'm going to call it today. And your homework is going to be due on Wednesday. I had originally said it was going to be due on Monday, but I'm going to change that right now to where it's due on Wednesday. I don't want to rush through this. I think this is really important. Your homework is going to show up today. I'm going to go ahead and tell you that the system here. Let me pull it up. I know we're really running out of time, but I want to pull this up. So, oh, wrong one. So the idea is I'm giving you a system that's a little weird, but what I want you to do is I want you to see if you can take this system and assemble it, okay? I want you to assemble this system so it has, I said it has 4 nodes. Actually, it's supposed to be 5 nodes. I'll fix that. But the idea is this stiffness matrix will be 5 by 5. I want you to take this set of stiffness matrices and see if you can assemble it. This isn't going to be due till Wednesday, but it's really worth taking a look at and seeing if you can sort of attack it this weekend. On Monday, we're going to finish this matrix problem, and then we're going to start to dip our toes into truss land. That's all I have, everybody. I will see you all next week. Y'all have a wonderful weekend. We'll see you on Monday.